that Bennett was talking in his presentation. The outline of my talk would be an introduction. I will present our model and results and compare with other approaches that have been tried in the past, and I will try to draw some conclusions on perspective. Well, I will be interested in the crust, of course, and we will keep in the density region where we have nuclei separated and by a distance that is quite much larger than the radii of the nuclei, so we will not go very deep inside the inner crust, where our model could fail in some aspects that I will comment later. Previous calculations, as I told you, have been done for the pin of vortices to nuclei in the neutron star. The first was that by Epstein and Bain, and then more microscopic calculation by de Blasio and Elgeroy, and more recently semi-classical calculations, which are kind of intermediate between the more microscopic and macroscopic calculation done before. And I will quote also a vortex calculation in uniform matter, which does not include pinning to nuclei, but which are a good background for the presentation of my talk, that is this calculation made by Yuval. But first, let me remind that a vortex in uniform matter, let's say first, has an order parameter that has a dependence on the angle around the axis of the vortex. And this dependence is through the collective phase associated to the flow around the vortex, and is controlled by what we can call the vortex number. If this vortex number nu is 0, we have no dependence on the angle, and we will be talking about the ground state, no vortex. We can put 1, and then we will have some dependence on angle. A flux will appear, and then we will have a real vortex. But in principle, this number can be 2, 3, some number larger than 1. But these other vortices are kind of unstable. Well, the tendency is that in real cases, the only case that will be considered is the nu equal to 1. And in this case, nu equal to 1, that is the one I will concentrate, implies that our order parameter, our pairing gap, and also the condensate wave function has a parity which is -1, because the parity of this condensate is -1 to the nu that is determining the kind of vortex we are dealing with. So in our case, it will be -1 most of the time. And remember that we are dealing with a Fermi liquid, so it's made out of fermions, but that pairs in Cooper pairs, and these Cooper pairs are forming the condensate wave function. So these Cooper pairs have to give us the parity of the condensate. So these Cooper pairs will have parity -1 in our vortex when nu is equal to 1. This is an important thing for the rest of my talk. Let me remind how is a vortex in uniform matter. Uniform matter, the vortex line has a flux around the axis, and we have no dependence on z. So the only dependence is with respect to the distance to the axis. And with respect to the distance, we can observe different things. First of all, the order parameter, the pairing gap. The pairing gap has to be 0 just on the axis because it's angular dependent. So the only way we can obtain a unit number is being 0. but this gap will increase linearly when we go apart from the axis, and will increase until, when we are sufficiently far away, we reach the ground state, or the asymptotic gap, which is the gap of the condensate where we already have no vortex. So it's only in the surroundings of the axis that we obtain a depletion of the other parameter, and it grows linearly from the axis. We also obtain some depletion in the density, and we obtain, of course, a velocity field around the vortex. This velocity field, asymptotically, is the Onsager's formula, but as we approach the axis, this velocity is getting somewhat smaller until some maximum is reached, and then goes to zero just on the axis of the vortex.
But I guess the question is, how do you define this velocity? Because I mean, normally you think the superfluid is just having this 1 over r. Right? And
Yeah,
so
this is
that one. So this is just because. How is the velocity defined?
This velocity is obtained from the from our condensate wave function through the usual equation. Somewhat far away. So we will have the occupation factors of the condensate, which will depend on the azimuthal.
Okay,
angle.
it's the total current
This is the
divided
total
by some ambient density.
Exactly.
So it's not really the superfluid quantity. There's not some sort of superfluid density down there.
Well, this is the total superfluid density. Yeah.
No, it's the total density.
Density.
Right.
Total density.
Because,
Right.
I mean, really the velocity field is 1 over r, come what may.
Well, if you think into components, you can say that the superfluid component
The
disappears.
superfluid momentum is always 1 over r.
Okay, so this is the average.
Right. Okay. But it's really because there's a lot of normal stuff in the core which is not taking part in the
In the
motion.
Well, this is the aspect of a vortex in uniform matter. But then we have to put this object in contact with the nuclei, which is the main object of my talk. And 2 days ago, Enrico Vigetti told you about the pairing gap in nuclei, where we know that we have pairing gap outside the nucleus, another pairing gap inside the nucleus, and some proximity effect and some smooth connection between them. So typically we will have a smaller gap inside the nucleus than outside. This is also what happened to the vortex. The vortex has a smaller pairing gap close to the axis than in the, let's say, asymptotic region. But a smaller gap means a smaller condensation energy. So we are losing condensation energy in this region, close to the axis, and we are also loss of condensation energy where the nuclei are, where the nucleus is present. So as Bennett was saying before, general wisdom is that if we put all these two regions together, where the depletion of the gap occurs, we will save some condensation energy, and this will try to give a global gain in energy and make an unstable situation with respect to the situation with both objects are far apart. So in our calculation we will try to evaluate this difference of energy. Of course, also the kinetic energy will be modified by the interaction between these two objects. So we define the pinning energy in the same way as Epstein and Bain did, and we can easily understand it in this little scheme. We will evaluate the total energy of the vortex line going through the center of the nucleus and compare with the energy of the nucleus alone. This will tell us how much energy we have to spend to put a vortex on top of the nucleus. And then we will compare this with the energy we have to put on uniform matter to create a vortex. And the difference between these two will tell us whether it is better to have this separate configuration or whether it is better to have some free space with uniform matter, but all the two objects together. So this difference will tell us how much we gain with this superposition of vortex and nucleus.
There's also there's the bulk energy gain because the gap is smaller inside the nucleus, but also when you try to get the vortex onto the nucleus, you are changing the shape of the vortex. So
Yeah.
the gradient energy cost is, I guess, the balance between that.
Yeah,
cost.
this has to be taken, but it's a key point of the calculation. So this is the conventional wisdom. Pairing gap is smaller inside, vortex destroys pairing close to the axis, and if we put both things together, we should save some condensation energy. And in the Epstein and Bain calculation, they were precisely calculating what I already showed you, the gap along close to the axis and how it behaves when we go apart. They were evaluating the condensation energy, also the kinetic energy associated to the vortex, and studying how this depends on the distance between the nucleus and the vortex, which would move like this. When we are far apart, when our vortex is far apart from the nucleus, place it at the origin, we have the asymptotic energy of the two systems, but as we approach, we can have a diminishing of energy because of the saving of condensation energy, but sometimes, depending on the density, we can have also the opposite, because the saving in condensation energy would not be enough to compensate the increase in kinetic energy. But on average, for a, let's say, wide region of densities, they obtain, as you can see here, a stable situation for the pinning configuration.
In the calculation you're going to present, you only give 2 points.
Yeah, in our calculation, we will compare this situation and this one, because our calculations are microscopic, so numerically are complicated, and we want to keep the cylindrical symmetry. So we just, by now, make a two-dimensional calculation, meaning we only can calculate these two extreme points. But still, this will give us an important information. So our model is a cell in which we can have a nucleus or not, and in which we can have a vortex or not, or both. And in any of these 4 situations, we will solve the Hartree-Fock-Golikov equation, meaning the BCS, essentially. And I will skip the technical details, only remind that we are using the cylindrical symmetry for convenience. Our box typically is 30 Fermis, which is large enough to describe both nucleus and vortices. The calculation is going to be self-consistent in the sense that the mean field is left free to adjust to each of the situations. For the mean field, we will use some standard scan force. We will use 2 kinds of scan forces just to check the dependence of our results on some important parameters of the scan force. And for the pairing interaction, we will use a simplified version, which is a contact interaction, but with a density dependence that resembles very well what you obtain when you use a more realistic argon force. Using contact interaction is also convenient for numerical purposes. And just as a kind of check, here is what we obtain for a vortex in the cylinder without the nucleus. Inside the cell, what we could call a vortex in neutral matter, uniform neutral matter. And we reobtain the results that Ju and Bulgak were obtaining in the paper. So we have the velocity field, the pairing gap and the depletion at the axis of the vortex. But now we put the nucleus. We put the nucleus and we can look and add to the pairing gap as a function of the distance to the axis. And here it's clear that we have different situations. If we are far apart from the nucleus, which is this one, don't pay attention to the colors, are not in correspondence. If we are far apart from the center of the nucleus, we reobtain the free vortex because this region is not influenced by the nucleus. But as we go closer to the center of the nucleus, and if we place in the equatorial plane, we obtain this other extreme curve. And in the middle, we have a smooth variation. And this is telling us that the pairing, the other parameter, is destroyed inside the nucleus. The nucleus have already a small gap, which is this one. But now, inside the nucleus, in the equatorial plane, it is completely destroyed. And, well, this variation is just due to the curvature of the nuclear surface.
And the nature of oscillations. Your curve, oscillates. Why?
Well, are not that important, but in principle you can obtain oscillations in the pairing field, even in the free vortex case. You also obtain some which are related to some bound states inside the vortex.
There's no enhancement in pairing from surface effects?
This is not taken into account in this calculation. I will comment later. This is the next generation of calculation we would like to do. To this point,
I was going to say that the oscillations here are presumably in large part due to the shell structure within the nucleus.
also,
Right. Discrete.
as far as you have some discrete levels, you can some oscillation.
No, but you just said that you also have them in pure uniform.
Yeah, in pure, you also have
Also,
some.
Yeah,
also
but
without
yeah.
For-
they are present also without the nucleus.
This is due to discrete levels inside the core. So you obtain a potential.
Well, is it? At the upper ones, but the lower ones where the wiggles are much
Yeah,
greater.
then you have
due
the
to
nucleus.
the discrete shell effects. And
What does the negative delta?
This is a pairing. This is the pairing field. It's not the pairing gap. Okay, the pairing field, which is dependent on R. Of course, if you make some average, then but the important thing here is that we can see that the pairing gap has been suppressed within the.
I'm sorry, you probably said it. Which nucleus?
This is Z equal to 40. It's a kind of negligible cluster. Yeah, and to the velocity field, this is the result we obtained naturally when we are far apart from the nucleus, the free vortex in uniform matter. But as we go closer to the equatorial plane, we obtain a velocity field that drops as we find the nuclear surface. And then essentially zero, some small oscillation again, but essentially is zero.
What does it mean, get negative velocity?
Well, negative velocity is a very residual part, but would mean some counter motion in some of the regions inside the nucleus. That is kind of very residual.
Differential reflection.
We have not gone into these details, but the means motion in the opposite direction.
You said that the pairing is destroyed in the volume, but in fact, if you show the figure before, it's really destroyed, I said, within a big extension that really covers the surface of the nucleus, not only the interior of the nucleus. Remember conventional wisdom. Conventional wisdom said, oh, we gain condensation energy because we destroy pairing where it's small in the volume. But you know, this pairing gap, as I also showed the other day, is really position dependent. So on the surface often is where it takes the largest value. So you already see a big difference compared to the simple-minded approach. There.
This
Qualitatively, I mean, the fact that you expect, you know, enhanced gap near the surface, and also, so at first you would naively guess that as the vortex gets close enough, that it begins to touch the nucleus, so to speak. There should be some repulsion. I mean, that, you know, you're actually, it's costing energy because you're messing around, you're actually going to a higher gap region. And also, the gradient terms are more important there than the bulk terms. So one would, you know, just based on that, I would expect that at first you would see repulsion at some large distance. And then as you get closer and you tap into the condensation energy, you may get attraction. So I suspect that there is, at very long distance, the interaction is repulsive.
This can happen depending also on the density we are talking about, because the profile of the pairing gap through the nuclear surface could do as you mentioned. But for most of the densities, and as you could see in the Epstein-Barr calculation, the curve is kind of monotonic, but it could happen. But in any case, we are calculating only 2 points. We are completely unable by now to say anything about it. But just to stress what Enrico was commenting, here you see what we obtain for the pairing gap in the equatorial plane and what is far from the nucleus, meaning the uniform matter vortex. And we made the game of just shifting in this figure on top to the new gap at the equatorial plane. And as you can see, the rise of the pairing field is almost exactly the same that we have for the uniform case, but exception made of the point in which it starts. So it's like if the vortex started at the surface of the nucleus. So the vortex core has now a region, a very large region of non-superfluid matter, and it develops from the surface of the nucleus. This is what this figure is telling us. So the general wisdom was that we were going to save condensation energy, but this shifting of the origin of the vortex is incompatible with this general wisdom, because now we have already the condensation energy that the vortex by itself is losing due to the smaller gap. But in addition, we have now all this region, which in the nucleus was small gap, but now is zero gap. So this effect of expulsion of the vortex up to the surface of the nucleus is increasing the loss of condensation energy. So in principle, it will go almost always against pinning.
So it's an effective vortex flattening.
Exactly. But, sorry.
Vortex obesity.
But now we have also together, at the same time the gap is diminishing, we also have a truncation of the flux, of the motion around the axis. For the uniform vortex, this motion was sizable until very close to the axis, this situation, 3 Fermis or so. But now, when we are in the equatorial plane, this flux velocity drops as we find the nuclear surface. So, from the kinetic energy, we have a gain of binding energy, because now our vortex develops less kinetic energy when it's placed at the center of the nucleus, when the axis passes through the center of the nucleus. We are saving all this kinetic energy. So, from our calculation, the pinning balance, the pinning energy balance, would be condensation energy is against, but saving in kinetic energy is in favor. So these are the two main components of the energy balance, as I will show you now. But before going to the energetics, let me try to explain why this flattening of the vortex. As I told you in the beginning, the Cooper pairs in the vortex situation must have negative parity. So if we want the vortex to develop in the nuclear region, we have a difficulty, because shell effects tends to separate parity single particle states in the nuclear shell structure. The positive parity and the negative parity are separated typically by 8-7 MeV. So if we want to construct a Cooper pair inside the nucleus with negative parity, we should combine levels that are far apart, much larger, an energy distance that is much larger than the pairing gap, which is typically 1 MeV, 2 MeV. So constructing a Cooper pair with negative parity in the nucleus is very difficult. And in this figure, I'm showing the phase shift of the single particle levels in the continuum, because we have our Fermi energy in the continuum, as a function of energy. And here you see positive, negative, positive, negative, positive, negative parity, and you can see the change in phase shift indicating the presence of resonances in the continuum. It's on top of these continuum resonances that we have to construct the Cooper pair inside the nucleus. And as I was telling you, the distance in energy between positive and parity state are larger, much larger than what the pairing gap can connect, the pairing interaction can connect. This depends, of course, on the effective mass of our beam field. That's why here I'm showing you two different cases, a small effective mass case and a larger effective mass case. And also depends on the density, on the average density we are talking about. So we expect that different forces will give some different expulsion or flattening of the vortex, and also we expect that change in density, this will also change.
This resonance, I think, what you mentioned that, isn't it? When you discussed your coupling with phonons. So this is exactly the point, isn't it? That you feel the shell structure of the nucleus, even if you are in the continuum, up to a certain extent.
Right.
Because here density means you raise your, say, Fermi energy. At some point, of course, you are so high that the nuclear well is not felt so much.
Yeah.
So that's why there is also this density dependent in these calculations. So the effect of resonance is weaker when you go deeper into the star and the Fermi energy increases compared to the bottom of the well. So that's the tendency.
And here is an example of the calculation with a low effective mass and a high effective mass mean field. And in the case of the high effective mass, where resonances are closer, the pairing up, even when we have the vortex on top of the nucleus, even going to zero is not so dramatic as in the case of a low effective mass. So, in fact, the density of levels in the continuum is playing a role in this fattening. In this case, it's a strong fattening, let's say, a drastic fattening. Fattening in this case is a smoother fattening. Just as a matter of check, this is what happened when we place mu equal to 2. Remind that the parity is -1 to the new power. So if we think in or calculate a mu equal to 2 vortex, in this case, the parity of the Cooper pairs must be positive. And then there is no difficulty for the pairing interaction to construct the vortex inside the nucleus, because we are on shell, we have at the same energy many similar parity states to be connected. And in fact, in this case, you don't see any strong effect going from the equatorial plane to far from the equatorial plane. So the effect of the nucleus is in fact much less due to the fact that now for positive parity Cooper pairs we can construct with available resonances the Cooper pair inside the nucleus. Now here I turn again to nu equal 1, which is the interesting case. And here I'm comparing the radii of the vortex in uniform matter and in the equatorial plane. We define the radius where the gap reaches or covers 90% of the asymptotic value. And as you can see, there is, as I was telling you, a flat, an increase, a strong increase of this core in the equatorial plane for all the forces. So this is a characteristic. This is a characteristic of that we recover with all of the forces. Though in the large effective mass forces, as I was telling you, the gap is able to go inside the nucleus a little bit more than with the low effective mass forces. And here again, for one of the forces, here we have the radius of the vortex at the equatorial plane compared to the case of the free nucleus, and compare to the calculation of the semi-classical models. Of course, in a semi-classical calculation, you don't take into account the shell effects. And in fact, they don't show this important increase on the rate. So this effect is completely absent in a semi-classical calculation. And this is important to understand the different results we obtain with respect to the semi-classical. Here I'm plotting the total pinning energy, with the low effective mass, with the high effective mass, as a function of the density. And from our definition, negative energy means pinning, favoring pinning, and positive energy means anti-pinning. And for very small, very low density, we obtain pinning values which are of the order of 1 MeV, but for a very small region of densities. We could say that in most of the cases, we obtain anti-pinning of the order of few MeV for these forces, low effective mass forces, and recover some pinning for large densities. In the case of high effective mass, we also obtain some pinning at low density, but at large density we keep on finding anti-pinning. And the reason for this is that as I was telling you, the behavior of the vortex inside the nucleus in the high effective mass case is different from that of the low effective mass. But in general, we can say that we obtain pinning at low densities and anti-pinning essentially in the rest, and of the order of 1 MeV as much in the case of pinning, and about few MeVs when we obtain anti-pinning. And this is a strong contrast with what is found in the semi-classical calculation. As I was telling you, the semi-classical calculation, the picture is just the opposite. The condensation energy is driving the pinning process. And in fact, it's almost exactly the opposite. In the semi-classical model, one obtains anti-pinning at low densities and pinning at higher density. But it's not surprising. I mean, the mechanism is just the opposite. So you say it's a natural consequence of the shear effects in our microscopic result. The thick line is the total pinning energy, and here we have plot separately the condensation contribution and the kinetic energy contribution. This is the condensation energy, which is giving anti-pinning, and this is the kinetic energy, which, as I said before, is the saving in energy we are obtaining in our calculation. And while in the semi-classical case, it's just the opposite. The condensation energy is the one giving most of the pinning energy.
One question, but first, so the condensation energy, I mean, both the flow and the condensation energy are very large when you subtract them, no? So it's like if you move a little bit any of this curve, then you can get the opposite result.
Are delicate calculation. In fact, here I'm plotting the condensation and the kinetic energy, or the other way around. But just for illustrating our result, the thick line is obtained evaluating the Hartree-Fock-Volvo Hamiltonian, which is a microscopic Hamiltonian. So we just evaluate this functional. But we can produce from our wave functions the condensation energy and the kinetic energy. The sum of both is this number, which is not the total thing.
And why do we get something different?
Well, because these are not the only effects. We have distortions of the redistribution of density inside the nucleus and also inside the vortex. So this is not the whole story. We have other internal potential energies and microscopic kinetic energies that contribute to the total Hartree-Fock-Volvo microscopic result. But it's a good guide. I would say that is telling to you which is the trend of your microscopic calculation. But this is just for interpretation purposes. The real number is the thick line. In the case of semi-classical, is just the summation of both.
Have you done the calculation for other nuclei?
No, because in the density region we are analyzing the Nagel-Botren nuclear piece. This piece is always very close to zirconium, so we get fit to this case. But you say because you mean larger nuclei, smaller nuclei, for example, impurities in a way with respect to the
But here the mean field is determined by by the interaction you are using. It's not that you put a nucleus, say you just say, I have number of protons in this cell, and then a density. And then you run your calculation. So it's not, so the only input is the number of protons in this
Yeah,
calculation.
you say different.
And the
number of
density and average density you want.
Yeah,
I mean,
could be.
that's the only thing you.
This is
you
just
talk
for
about, you know?
this case, which is from the negative terms.
And we have D by 40 for a big range of densities, no?
Yeah, it gives 40, 50.
A change, but it's easy.
So I could conclude saying that we have solved the Hartree-Fock-Bogoliubov, and that finite size shell effects are rather important because it changes completely the picture. And as pinning is concerned, we have found pinning at low density, but almost systematically anti-pinning for higher densities. As I told you, we are calculating only 2 points. It would be very interesting to have a more precise description of what is happening when the two objects are close, but it would imply 3D calculation, which is heavier. And important, we are not include medium polarization effects. This is a mean field calculation. And as Enrico was saying the other day, a medium polarization changes the gap both inside and outside the nucleus. So all our results could be affected by this fact. Probably not the main message of this talk, which is shell effects, making possible the construction of a Cooper pair of negative parity inside the nucleus. But the final energetics could change somewhat. And another work for future is to calculate this kind of pinning energy for pasta phase, where we have spaghetti or lasagna geometric configuration. And as Bennett was mentioning, in the core where also the flux are going to be important. And just let me finish with a final remark. For the study of this coupling to surface, of course we have to calculate the surface modes of the nucleus inside the Fermi liquid. And here are one of the first calculations we are obtaining. This is a calculation of the giant resonance and the low line of this zirconium nucleus, ignoring the states belonging to the continuum, to the Fermi liquid. When we allow to talk each other, you can see that the properties of the nucleus are changing quite a lot. The giant resonance is acquiring a much larger width, which we can connect with the fact that this giant resonance is going to have a kind of damping due to the emission of waves in the continuum. And also there is a strong modification also of the width, the low line is changing. So these results are telling us that a strong interaction between the superfluid and the nucleus is present, and that has to be taken into account in any calculation where we want to describe how these collective modes appears in the neutron star.
This kind of effect, I think you say, in some way is missing from your consideration, isn't it? Because your superfluid phonons do not really, say, excite internal degrees of freedom of your nuclear cluster. And you see here that they may be relevant.
But you got to look at the energy scale there. We are interested in energies of order 10 to the minus 2 MeV. Okay. The question is, this is a, if you are trying to apply this to what I was talking about, you get the wrong picture. If the nucleus has extremely low energy excitations of the order of 10 to the minus 2 MeV, yes, we have to worry about it. my assumption was such excitations are going to be gapped in the nucleus, so there's going to be shell structure that prevents such excitations. But who knows, when the nucleus gets really, like in the plasma phase, you get a very big size object, then there may be excitations in that object that are of order 10 to the minus 20. Then things get complicated.
The very low energy spectrum here, this is influenced by your box boundary condition?
Well, we have tried different boxes and some details depend, but not not the main aspects of the calculation. In this case, even less. In this case, we are making an RPA calculation including only the resonances, and the resonances are when the sound does not depend on our book. In this case, some details, but not the general trend. I mean, the increasing of width and so on. Okay, thank you very much for that.
I'd stress from what I was saying in my talk that what you were calling anti-pinning or non-pinning, as long as the length scale of the interaction is comparable to the nuclear spacing or some fair fraction of that, you will have pinning in the interstitial regions, just because you're basically turning the potential inside out, and the vortex can find places where it prefers to be energetically. So the curve you showed would actually, in my picture, have pinning basically everywhere.
Yeah, I'm saying pinning in my context of a single nucleus.
If there's a region, a transition region from pinning to anti-pinning, and so there's a layer in the star where the energy is essentially zero, does that have any dynamical consequences?
I couldn't walk and listen at the same time. You said in a transition region where a change is signed?
Yeah.
Niels, is that a set of measure zero? I don't know. My expectation is that it's just such a small region, such a small range in density that there's a little effect. Imagine dividing up the crust into regions where it's one fairly large magnitude versus another magnitude of different sign, and that's what controls everything. But I can take the picture I put up here. If we just take little places where we cut out the pinning where it switches sign, it's not going to make much difference as to what the total force per unit length is on that vortex. And that's also true even if we don't believe in vortices that traverse the entire length of the star, but we chop it up and give it some complicated structure it's over macroscopic lengths. It matters.
How much deformation is, I mean, the nucleus deforms in response to trying to house this vortex. How much deformation is there?
We have to look at this, looking at the density distribution in the equator or along the axis. There is an effect, but it's quite tiny. Remember that the vortex in the free vortex in uniform matter produce some depletion at the center, but it's a very small scale thing. And this is taken into account in our microscopic result. So our microscopic result counts every single little change in the mean field and in the length.
Any other questions or just done?
You mentioned spin orbit forces at the beginning. Can you say
No,
you do not
this-
have them?
We have not included spin orbit also because of CPU time.
Yeah.
But-
But you find shell effect are important. So
Yeah, I have an answer for that. So if you have a spin orbit, your level will split. But the requirements for the Cooper pair formation will imply connecting the down-going level with the down-going level and the up-going level with the up-going level. So in the end, you will still have a large gap. and the intruder state cannot couple for the Cooper performation with the outgoing level of the last shell of occupied last shell. So you don't. I mean, the spin orbit will not change this requirement, this difficulty of the large gap, which is the gap between resonances. This is just argument. We have not made the calculation, but that's why we think the result will not change much because of spin orbit.
One question about this the parity, this quantum number. If, for instance, you take nu equals 2, does this mean that a vortex line carries twice the angular momentum of something like this? No? And so if you put nu equals 2, this has a higher energy than nu equals...
Yeah, it has higher energies and these higher new vortexes are unstable and usually decay in the nu equal 1.
And so could it be, maybe some subtle effect that nu equal 3 or 4 could have a lower energy, or?
Well, larger the nu,
It's always
larger is the
increasing.
energy of the vortex.
Wait, just to get a clarification. So when you put a nu equals 2 vortex on a nucleus, it's actually favorable, right?
It's almost transparent to the.
Yeah. So you don't
to the
really.
nucleus.
So if you have anti-pinning,
Mhm.
when you ask what is the energy of a nu equals 1 vortex on a nucleus and a nu equals 2 vortex,
Yeah.
you will find the nu equals 2 vortex is stabilized by the nucleus. Because in one case you were losing energy because you had to distort the nucleus.
Yeah, there could be some energetical
You
complications.
might find some parameter space where
Okay. Yeah.
nu equals 2 vortices. Nu equals 2 vortices are the favored state when you have a lot of nuclei.
I think we could do.
If you want lunch, sometime today, you should be quiet then.
And what happened to the nuclei which are outside the core? So you still have the flow of neutrons going through them. So you produce a force on
Outside the core of, you mean of the core of the
core of
the
vortex. You have all this flow of superfree neutrons and there are many nuclei, so this flow goes through the nuclei.
Well,
What happens there?
the asymptotic the asymptotic
I had a
values.
good breakfast today. I knew this would happen.
Did I bring in some cookies?
If you
All
are
right,
jelly,
we'll survive with cookies and coffee.
If the density we are placing is not very large, the nuclear cluster are sufficiently large apart for not having a strong influence from this single nucleus. So you can think that the other nuclei surrounding are in the uniform flux.
so they see the flow of neutrons through them.
Yeah. Yeah, but this is already there. I mean, we are looking at the difference between being in the interstitial situation and in any case, the effect of a single vortex on neighboring nucleus is very, of a single nucleus is very, very small. This was evaluated in the semi-classical model, which is rather okay when the vortex is far from the nucleus.
This is an interesting point is if you think that the pairing gap is really reduced, you could have vortices maybe larger than that. Then in this case, maybe this Wigner size approximation of take one could also be work not so efficient. Because this is a typical radii for these pairing gaps. So but if you reduce the pairing gap and you change the coherence length of the system, then your pairing, in principle, the vortex you calculate could be even more extended and reach, say, other. Because this is really, I don't know if people here appreciate it, but here really, this is the basic uncertainty in all this game. Pairing is possible reduction, or it acts in many different ways.
In the interest of an eventual lunch, perhaps we should move on.